Testing. Okay. Okay. Testing. Testing. Hello? Can you hear me? Okay. So I guess we should start. So today's goal, what we'll be doing would be we'll finish off this probability, and then we'll start the random variable, and I think we will have a lab section on the this Wednesday. So make sure you go to the lab, but it's fine. I mean, the same building anyway. So just make sure that you go to the lab. So let's very briefly review what we cover in the probability, and then we'll go to the part we haven't covered. Okay. So what is probability? Just to remember, we start to begin to define what we call a random experiment, which said you can repeat things, and then we basically know what are the possible outcomes, but we just don't know which one comes out. And the classical way to define probability is there's a ratio, which is defined as how many outcomes that the favor of the event over what total number of experiments you have done. And the what is intuitive is if they toss a fair coin, and then half of it will be tail, half of it will be a head. If you repeat this many times, you can do experiment at home by yourself, and you can convince you this is something is rather stable. And the more experiment you do, the more likely that you will see is very close to half and half. So because of this physical observation, this probability would make sense. Okay. Of course, when we talk about probability definition, we can abstract from that. But the reason why we can abstract from that because we have some foundation from the physical world that is true. And we then define the different operation on the event, right? The intersection, union, and complement. And then we define what is mutually exclusive and exhaustive, just to remind you that what is mutually exclusive means that if two events are mutually exclusive, then if one is true, the other is not. Okay, so it means that they cannot happen to be true at the same time. And the other one is exhaustive event, which said either of them must be true, and both of them can be true. What is rule is both of them are false. Okay, so the mutually exclusive is rule out both of them are true. Mutually exclusive is exhaustive is rule out both of them are false. Okay, and when we talk about if the events are mutually exclusive and collectively exhaustive, means that we call them partition. Okay, you just cut them out of the sample space, each small part, and none of the part are overlapping with each other if you talk about the Venn diagram. And with axiom of probability, and the idea is we do not rely on the definition of random experiment because it's not very precise. What do you mean by random experiment many times? Okay, so the definition will be 3 axioms. The first axiom said probability must be between 0 and 1. And we know everything in the sample space, so probability sample space is 1. And the last one is the structure we impose, which said if events are mutually exclusive, then probability of that event will be the sum of all the probability of all the outcome. Basically said if you consider event, you cut them into small part, it's a partition, right? And sum of all these small parts should be same as the whole, okay? So that is something that we expect it to be true, okay? And here exactly is something more technical is we cut the event into different parts. We allow it to be infinite many. So this is rather technical. So it's not needed if you don't understand, but if you care about continuous random variable, actually we'll be doing today, some of them that we will see that is required. And there are several rules coming out from probability axioms. First one is complement rule. The reason why is if you want to figure out the probability of A would be you can sometimes find the complement and take the 1 minus that one. We're not going to go for example, but this will be the way you calculate. Okay, don't worry. A lot of things seems very abstract. You will do assignment 2. At that time, then you will be able to do more. Okay, you learn more. And the other one is addition rule, which basically coming from basic geometry you learn in the elementary school, right? It's just saying that look at the very last one, okay, which basically said A plus B, the probability. If you subtract from the intercept, will be the union, right? This is the graphical meaning. If you have the purple circle plus the red circle, right? Then you overlap the paint area, take away that one, will be the glass style area over there. Okay, so probably it's not something terribly difficult. And the next one will be the third probability rule. Is basically saying probability A will be, you can decompose in 2 parts, A with B and A B complement, right? Basically just use B as a cutting, right? Because B and B complement by definition is mutually exclusive and exhaustive, right? So this partition. And idea is like this, it's like A, and then you can have part that with B, which is the middle part, and without B is the part that without is a pink part, right? So the red part, okay? The red, this part, right, plus this part is the whole circle. So that is the idea behind this rule. Okay. In general, if you have a partition, it's also the same, right? You cut to many parts, the same thing. And the last thing we talk is about odd ratio, which said why we don't talk about that, because this is how these in probability, the odds ratio related to the odd in the real world. When we're betting, we talk about odd is 4 to 1. Indeed, if this is odd, if this betting is a fair bet, then it implies what's the odd ratio against the event, because this odd ratio is the against A is exactly what you see in the real world. Okay, but of course, in the real world, there's some money, the profit that the casino is going to make. So it's not exactly that one, but if the casino is competitive, in that case, the odd ratio would be, you can use the odd ratio to infer how people think about the likelihood of the betting event. Say, if you look at the UK soccer, I guess this is something that is betting is rather competitive. In that case, you can look at the odds of what the team A is getting, and then you can estimate from people's point of view how likely a team is going to win. So that is the usage of probability to look at the market and try to infer back how likely things are going. Okay. And the next thing is a little bit go slow, because I think we just stopped from the Bayes theorem, so we just started again from the conditional probability. and onward. Okay, so just to remind you the definition of conditional probability, which said the probability of A have a vertical is usually called given. A given B or A conditional on B will be a fraction where the denominator is probably B and numerator A intersect B. Okay, the numerator is obvious because we say B has happened, so the two part, right? A will be A intersect B and A intersect B complement, right? That actually there's two part, right? If you remember the third probability rule, right? It's A intersect B and A intersect B complement, but A intersect B complement will be zero because we know B is true. Okay, so that's only relevant part we know. And the denominator is probably B because the reason why we have divided by probably B because we know now the sample space is only consists of B, right? So to satisfy axiom 2, which said the sample space must be 1, you must have divided by probably B. Right? The reasons being that is suppose event A is same as event B, right? This should give you the probability of B given B should be 1, right? So then everything will go back to the correct form. Okay. Of course, you can do a more rigorous proof, but that's the idea behind. You just because B is true, so you have to consider only A intersect B, and because this one you have to normalize to 1. Okay, so that's why everything become because the sample size shrink, so you have to derive by probably B to get the scale correct. Okay. So we have done all the examples and things. So the next one will be the multiplication rule. So this is also a rather important rule, which said the definition of the A intersect B will be A given B times B, or probability B given A times A. So there are two different ways to decompose it a intersection. Okay. So there's a lot of benefit of doing this is because of sometimes A and B are temporally related. Okay. And say in the first one, why you use it is because something B is happened before A. Okay. And when B happened, A will changes. Okay. So that would be easier way to do. So the example would be, this example is like you draw the balls, two balls from an urn. And do we call that once you draw the first ball, because without replacement, the urn has changed. And depending on what the ball you drawn on the first time, that will be changing in the next one. So that's why when you calculate the intercept, it's easier sometimes to do it this way, right? Of course, as you can imagine for this question, you have 6 balls. Actually, you can list out all the possible outcome, which is 36. Right, because you can draw a table, right? But imagine if it's not about 3 by 3 balls, you have 6 by 6 or 10 by 10, then it's not easy to do it. So it's much easier to do it in this way. Okay. So that's the reason why we need to learn this, is because a lot of time when you calculate things, it will be happen to be something this thing would be doing, right? Especially if we talk, for example, consider engineering problem or other problem, it will be what is happening will depend on what happened before. So that is, I think in finance, that's something we usually do. And the next one is talk about independence. This independence is important in the sense that we want to know, say, actually this more or less we are doing this for the second half of the class, right? We want to discover the causal relationship, right? We want to see whether how A and B are related, right? Just to remember what are the recent things talking about. Okay, say now people talk about whether we should take the third doses of the vaccine, right? So probably you want to see, for example, whether A is the rate of transmission or hospitalization rate, right? And B is whether you take the third dose of the vaccine. right? Then that will make a difference. So people talk about the drugs that might kill the COVID, then also the same idea. Okay, you want to see whether they're different, right? Whether B would be meaningful in this case. And if the most strict sense is look at this, look at data, right? If look at two group of people, if those people with the first dose of vaccine and those people who don't, then you can see the difference, right? And if there's no difference, of course, you can say you safely safe. The first dose is not very useful. But the problem is in the real world, there's a lot of random error, right? There's when you collect people, not all the two group of people are identically the same, right? Different ages, different gender, or different health condition in the beginning, right? And you want to see, but you really want to show it. That's why you have some error when do sampling. And that's why we need to learn probability. We need to see how they're different, okay? But at the end of the day, what we are doing for the probability, this class is basically more or less this equation, but we can go deeper by looking at the equality and what happened if they're very close, right? So suppose this is 0.9, this is also 0.9, then it's fine. But what about is 0.91? What about 0.88? What are you going to do, right? So that is the idea when you how close when you consider close, how different you should call it different. Okay, so that is the main idea. Is that basically the whole course is about. But then we will go into more detail. Okay, but just for the moment, you just need to know when you will call the independent. Okay, but of course here we don't have data, right? But I mean data is like you use the classical idea of classical differential probability, right? Define probability as the ratio, right? So now we are going to the very last important formula. We talk about this, and then we go to combinatorics. But this is very important. It deserves us to go a little bit slowly. So if you can follow, I just can repeat it more times. Make sure that you're okay. But so far, is there any question? Is that okay? Is that okay? So I guess we go to the most difficult part of so this it's a little bit trickier. Is you can see it looks confusing. Here is like the price B given A, the posterior A given B, and we're talking about. And just bear with me for the moment. We'll talk about this in a more concrete example again. Here is where the probably supposed B is bigger than 0. Okay. Otherwise, this doesn't mean anything. What's probability A given B? So condition on B was A. Okay. Can be written as we're similar to the differential condition probability. Okay. The denominator is probability B, and the numerator is A intercept B, if you remember the formula. And here we just use the multiplication rule. We can write B given A times A. Okay. And okay, so why we care about this formula? Because this formula is very useful for what we call the statistical learning, or how we learn from data, right? So as well, actually is also one of the reasons why we learn statistics, right? Because statistics is like look at data, we update ourselves, right? And we learn more about things from the real world. That's why we look at data. And let's go back to this example. I think this is the most useful example that you'd be thinking is we have a situation, actually what we see in the situation today is we have a population that is infected by disease, okay? And we have some knowledge about how many people having this number, okay? How many people have this? It's 40% of people are having a disease, okay? And now the question is, we have a medical test which is imperfect, okay? If this medical test is perfect, We don't have any static problem. Okay, there's no error. Okay, we test it, you had it, and done. Okay, but the problem is there's nothing in this world. I mean, unfortunately, no matter how good our technology are so far, is the test is always imperfect. Okay, even a guy with a disease, we only have 80% or 90, even 90 or 99. Even this would doesn't make a big difference. Even a 99% accurate. Okay, which means that if the guy has the disease, the test will turn out to tell you positive. Okay, and that will be 40% false positive, means that if the guy has no disease, okay, it may turn out to show you positive. Okay, which is possible. Okay, especially when we consider the case where people take the vaccine now, right? The vaccine now actually sometimes is a disease, but it's cured, right, from the Sinovac, right? And that can be because that thing remain in your blood system. So false positive is large is possible. Okay, even this is small, it still doesn't really matter. Later you will see if I even change this to 1% or even 0.1%, this problem will still exist. Okay, actually you will find you'll find your homework. I will make it more extreme, then you can still find the problem is there. So the main question, of course, is if I have a potential subject that actually have test positive, okay? So I now send him to the Penny Bay for 21 days, right? The question is whether I need to test them again or what, okay? So what we need to know is that I test it first and see how likely he is getting the disease, okay? And decide whether whether you want to go test one more and one more, how many tests you want to go before you confirm, okay? So let's go slowly. So let's call the event A is being positive, okay? And event B is being infected, okay? So now we can rewrite everything as above as the notation, okay? The probability B is 0.4, which means that without knowing any knowledge, I randomly draw a guy from this population. That's 0.4, okay? I have no knowledge about that guy because we know in the random guy in the population, actually 40% are infected. So if you're a random guy, that would be 0.4. Okay. And the next is the test is 80% accurate, means that if is infected, test positive will be 80%. That's 0.8. Okay. Okay. Here is I have the if the is not infected, okay, B complement, and then you get test positive is 0.4, which is saying that B, because not infected, you still have positive 0.4. Okay, so the question is asking if that guy has positive A, what for the B? Okay, so that is the main goal of this question. Okay, so as we do, the first thing to do is to use the all the rule we know to figure out what is not there yet. Okay, so the first thing we do is look at the complement rule, asking how many people are not infected. Okay, what's the probability likelihood? Because we know probability of infected is 0.4, so the complement 1 minus is 0.6 is those who are not infected. Okay, the next one we want to ask the question is probability of A. Okay, because B given A, the denominator is probably A. Okay, so we need to find that first. So just to remind you why we want to do this is because the formula here is the denominator is this one. Okay. Now this one will use the total probability rule. Okay, that decomposed in two parts. One is probably A and B, and A intercept B complement. Okay. So this is I think this is straightforward. Okay, and then the next part will be I will use the multiplication rule. Okay, to decompose it in B condition on B and condition on B complement. Okay, you may ask why I do in this way. Why I don't use B condition on A times A. Okay, the reason why I don't do the other way around because I want to find this. If you do this, then we don't know. Okay, so that's why we have to decompose in this way. Okay, And same idea here because we only know this, so that's the reason. And the other reason is why we decompose it this way, because the data we have is conditional on the guy who is infected. We know how likely they're infected, how likely to get positive or negative, right? Because this is some kind of experiment, okay? In the experiment, in the lab, we know we pick up people who are infected or not infected, right? And see the test result. So we have a knowledge about that. That's a power knowledge, right? But now we just pick a random guy, want to see, look at the test result and infer backward. So that's what we mean by the prior and posterior, okay? So when you calculate, it's 0.56 for this one, okay? So what is the meaning of this 0.56? Means that if you pick a random guy, okay, and do a test on him, okay, we have no idea whether he get infected or not, but just do a test on him, and he will have 0.56 probably that he has the positive outcome, okay? But it's not, doesn't mean we don't know how likely he got this or not. We just know if a random guy pick up in this environment, do a test on him, 0.56 he got the disease. So that's what the probably A means. Now the final step involves the definition of Bayes rule, right? So basically is this 0.56 is there, okay? And look at the numerator, just apply the formula, okay? Will be this one, but do note that what is this part, okay? This part, go back to the this one, is this part, okay? This part. So this is basically a fraction, right? Just like this denominator, the numerator, this guy, okay? So just try to make sense of this one again, because I think it's very important, okay? The number, you know, is 0.56, 0.57. It's not terribly important, but why this equation makes sense, okay? Or what does that mean when we change numbers, okay? So you can see, go back to the beginning. Suppose our text is so perfect, we never see a false positive, okay? Which means that if disease, you may have, may not, but if you have no disease, it doesn't have any problem, okay? If you have no disease, it's also negative, okay? Your test is rather accurate, right? In that case, actually, you would imagine if a guy has test positive, then he must have disease, right? Because negative, you don't have that, right? So in that case, it means that B of C A will be 0, right? Because this is the false positive probability, right? 0.4, right? If this is 0, right? This is 0, and it over itself is 1, right? So which means that if your thing goes very accurate, okay, this one drop to 0, you don't have any problem, okay? But as I said at the beginning, you never have 0, okay? Have something, okay? So the question probably is now asking is B complement, okay? B complement is what? B complement is like how likely people get infected, okay? And and if in this world, right, we see even now the pandemic, right, the number of people actually get infected is not a lot. I mean, it's not more than, say, in Hong Kong, it's not more than 1% of society. Actually, maybe 0.1%, I guess, right? I think it's like less than 10,000 people, right? Then compared to 6 million people, it's like way lower than 1%, right? And you can imagine this is rather big, right? Because probably B is the infected, right? B complement is not infected, it's very large number, right? This is maybe very, no matter how small, this one is pretty large, right? So this guy multiplied together it will be a very large number, okay? So it's always have this problem in the real world, right? Because your text is, no matter how accurate it is, because in the population, there are relatively few people have the disease, okay? So this your division, right? This term plus this term is denominator. This one is numerator, can be very small, okay? Cannot be improved very fast, okay? So that's why you can see in this case, before is it's random guys 0.4, okay? If you test positive, it's equal by 0.57, okay? So that means that it's not very accurate. Then you have to be very careful. Okay, so it's a little bit beyond what we're doing, but you can imagine the question is, okay, do we need to do one more test on that guy? Suppose I have that guy who tests positive. Should I do one more test on that guy? Okay, and a little bit beyond what we are doing, but you can imagine that how do you calculate the probability that he has disease, right? Suppose that guy have 2 positive outcomes. Okay, you test him. Okay, test him again. Okay, so what should be the calculation should be? The answer is actually very simple, but I don't want, will be now after one test, this is 0.57, right? So what is different from here is you redo all the calculation here, okay, except the fact that what you'll be changing will be this guy. Okay? You change what's probably B and what's B complement. Okay, because you're no longer a random guy. Instead of 0.4, you'll be 0.54, 0.57. And then if your calculation go on and you calculate the other number, you calculate if you have 2 positive outcomes, what will be the likelihood to get disease. Okay, and then you got one more and one more until you get your desired threshold that you will send him to Penny Bay. It'll be 90% send him away, right? So that is the idea. Maybe I should add that to your assignment. Then you have fun on it and you know how to do, right? That will be better. But that will be the idea. Okay. So let me repeat the argument here. Okay. Why you have 0.4 and 0.6 at the beginning is you assume that that guy is from the normal population. So when you draw it, that guy is 0.4 and 0.6 is following what you know. Okay. But if you test once, okay, then you no longer think he's 0.4 and 0.6. Okay. He's become 0.5. He's more likely to have disease is with 0.57. Okay. Then he don't have disease at the complement, right? And you can do all the calculation again, right? Because these are independent of what we know, right? Just only these 2 changes. Basically, this number, and do it again and again until maybe you are very confirmed it's 0.9. Then you just stop. Okay, you can go. You can whether you send him or not. Okay, and that is what we call learning, right? Because you keep doing the experiment until you get your desired outcome, and that is the meaning of statistics, right? Keep learning until you do better, right? And there's also actually you do on the online. Actually, you do all these things. You know, captcha. So when you try to go to some website or go to there, you to see whether you're human, right? They give you nine pictures, and they ask what is where there's an airplane, then they'll give you some picture. You can have to click, right? And likely you may not. Sometimes you can able to make perfect thing is okay visible, right? Sometimes you don't, right? And if you don't, then they will go on, right? And sometimes even you make all correct, then you don't go. You give the other set. The reason why is like this, okay? If this is so easy, the probability is not enough to make sure that you are human. You need to do one more set. And sometimes you make mistake. Maybe you're still human or then a machine, but you keep doing until the system believes you are human rather than machine. Okay, same idea here. So keep learning. The machine also learning whether you're human or not. Okay, so that is the idea. Okay, does it make sense? Any question? Okay, good. Anyway, you will be doing assignment on it, so you will see whether you understand or not. But this is so common. I don't think that would be a big issue because this topic, the Bayes theorem, is actually so important for those who do finance. It will be important thing. Accounting also the same thing, right? Actually, you do when you do audit, it's all the same thing. Okay, what you do usually the practice is, I mean, you every time at the end of the year, right? You want to audit the financial report of the company. So the company gives you something, you try to say whether there's something, right? And then one of the most important thing is like check the inventory, say for example. And in that case, then the big company, right? There's a many warehouse and many goods, and then it's impossible to check. Okay, so what you do is do sampling, right? what you do is just try to pick up certain things and see whether they're right or not, right? If you pick everything is in place, is correct, then fine. You are thinking, okay, that's fine, right? But you pick up this and you figure out one case is not, doesn't fit the data they give you, right? Then what you're going to do is to do more sampling, right? And if this time everything is correct, then maybe fine, right? But again, if there's one thing is not, or two is not, then you go on and on, right? If there's the same idea, okay? You just do things, learning, and keep updating your mind and see whether it fit your stuff, right? So that is how evidence being collected. But now at the end of before we have a break, let's continue with some counting. That is called probably so combinatorics. For those who learn computer science or other discrete math, that will be something the first chapter you learn. But that we're not going to that deep, but just give you some very brief idea on this, because we will need that for our some problem for the next set of slides, a random variable. Okay, so the first one will be something rather trivial, as you may say. It's called principal counting. Okay, so let's start with a problem. We have a mission to do. The mission have two tasks. Okay, and then we want to count how many ways to do this counting, how many ways to finish the task. Okay, and these two tasks is independent. Okay, so no matter there will be one different way to do the first task, and regardless of what way you do, okay, it's always two way to the second one. Okay, so and then what means that you can list them in two-way table, right? There's 1, 2, 3, 4, 5 for the first one, and for the column you need 1, 1, 2, 3, 4, 5 to n2, right? And n1 times n2 will be number of way to do it, right? Because for each way to do the first task, there'll be n2 way to do the second one, right? So then it's just multiplication problem. Okay, so it means that if you have k different tasks, and each task is have n way to do, then you just multiply. Okay, so there's nothing very deep here. So this is good to apply to this example. Okay, this fun example is something that I would do it when I was a student. Okay, go to canteen, right? There will be the choice will be you decide whether you get a rice or noodle. Actually, in my time when I was in this school is rice and spaghetti. Okay, there's two choices, and they ask you whether you want a meat, beef, or pork. Okay, sorry, pork, beef, or chicken. 3 choices, and there will be 3 sauces: black, white, and red. Okay, so the question is, how many different possible meals? The reason why you would be interested in this or are interested in this is because you don't want to repeat yourself, right? Although it's very boring, but you try to make sure that it's not going to repeat. And the reason why you don't want to repeat is because you're not, I'm poor, so you have to figure out ways to make your things rotate a little bit. Okay, so this means that we have to choose the dishes, which is the main dish is rice or noodle, which is 2, and the meat is 3 and sauce is 3, so it's 2 times 3 times 3, so which gives you 18. Okay, so that is pretty good, because usually you don't go to school every day. Okay, I mean your day off, so 18 is already 1 month, so 1 month you don't repeat yourself, so it is pretty good. Okay, if you, and you can imagine if they add one more thing, maybe lamb, then it will be more fun, right? You have your lamb, then probably you 2 times 4 is 8 times 3 is 24, so it's yeah, so it's pretty good, they're better, right? And you add one more, then it will be more fun. Okay, but that's how we do the counting. And the next one is related to the rolling a dice. Okay, and Again, we have syntax sample is how many face value, some of the face value less than 12, okay? And we know that to do the complement is easier, right? The complement is no less than 12, which is only 12, okay? And how to calculate this is this event, right? Because total number of possible event is 6 times 6. Why? Because principle of counting, okay? So that's why it's 1 over 36. And that's why we have 35 over 36. Okay, so that is the good thing about this counting, right? Here I have only 2 rolling, but if suppose you roll the dice 3 times, okay, then you know how to calculate. Okay, that means the counting, the multiplication is makes things rather easy to calculate. Now we will end this section with 2 more definition. This definition of counting is called permutation and combination. Okay, permutation is you have a bunch of objects, okay, n objects. You can imagine n different balls, okay. Each ball are different, and you want to put them on a line, okay. The question is how many different ways to put them on a line, okay. So the question is rather simple, in fact, right? There are n balls there, maybe different color, okay, or different number there, okay. The first box you want to put in the ball you want to put in the first box, right? With the n different way, with n balls, right? Each ball is possible. You render pick because it can be anything from 1 to n, okay, n balls. But once you put the first ball, what's left there is n minus 1, okay. How many different way to put the second ball is n minus 1. So that's why n times n minus 1. And then what about the third box? The third box, you put the 2 ball here, okay. What's left there is n minus 2. So that's why times n minus 2, and so on and so forth, okay. And from 1 multiply 2 up to n, we have a shorthand notation called n factorial, okay. It doesn't call exclamation mark, but it's called factorial, okay. The reason why it's exclamation mark is because you can easily check if you put 10 factorial is a very big number, or 100 factorial will be a huge number, okay. So that's why it's very surprising, okay. But there's no reason why they have exclamation mark, not question mark, not other mark, but they just use this way to do it. And in more general, instead of putting all n ball into the n box, okay, now consider a more general thing is you have n ball, but you have r box. Of course, r is less than or equal to n, okay. In that case, you don't put all the way, right? You just multiply until r, okay. The weird thing is r minus r plus 1. The reason is you start from minus 0, right? And minus 0 and go r1. So that's why this is a little bit look a little bit more, not easy to see, but have to twist your mind a little bit. You start from 0, okay. If you are coming from learning the programming from C or C++, you can't think from 0, then you don't have any problem. But if you're not, then a little bit tricky in your mind. But just you don't need to remember the formula, right? Just this coming from the counting, right? But at the end of the day, you just need to know this is called permuted NPR, okay? N object, you try to collect the R object out of it, okay? And do note that here is the order is important, right? So if you put the first ball in the first box, second ball in second box, okay, will be different from you put the second ball in the first box, first ball in this third box. Okay, that what I mean is if you have ball number 1 and ball number 2, you put the box here, 1 and 2 will be different from 2 and 1. Okay, they're different. Okay, and the question is, what is example we'll be using this? Okay, again, I motivate from my lunch. Okay, this motivation is from sandwich. Okay, and actually this is something Subway. Here Subway is not. I don't think it's very popular, but our Singapore there. So Singapore is a very popular thing because I think there's more foreigners in Singapore compared to Hong Kong. So what is the sandwich here? For the sandwich, of course, the first thing you have to say is the bread. Okay, there are many choices of bread. Here, I just make it easier. We just have 3 types of bread. It's like white Italian whole grain. Okay, the mini bread, but just make our life easier. So then you have to fill 2 of out of 6 ingredients. Okay, and if you notice, you put a sandwich. Okay, there. Okay, like this, right? First, you decide the bread. Okay, and the thing is, if you have beef here and your tomato there, okay, this is a one type of sandwich, but probably some people would think tomato here and the beef here is different, right? If you're picky, then probably they're different. Now the reason why is this, right? Because of gravity. Okay, if there's no, it's not in the earth, doesn't really matter, right? Because the beef, the juice of beef, you mix with tomato, then you think different, right? Here the tomato juice maybe stick with the beef. Okay, so people will say this are different. Okay, if you don't, then we'll be talking about the next slide. But suppose they're different. The question is how many types of sandwich you can make. Again, why I care about that, right? You can imagine, right? If you are not very rich, you have to eat some Subway and figure out that how many different ways to have fun, right? And we will combine the permutation together with principal counting to do this question. Okay. First, you need to decide what kind of bread is. There are 3 different types of bread. So that's why we're 3. Okay, that's why we're 3 here. The second thing is to decide the ingredient. Okay, the ingredient is you have 6 different possible ingredients. You have to put 2 of it, right? Basically, just like 6 numbers, you put them into a box. Okay, as I said, this is different from this one. Okay, so that's why you need to is 6 out of 2 is 6p2. Okay, and will be 6 factorial over 2 factorial. So you can see in this case it's a huge number, 90. Okay, you can imagine that is one. You can imagine you can do 1 semester already. So pretty good, right? You don't repeat yourself for 1 semester. You just go to this particular store, Subway, to finish. Okay, imagine you have drinks. Okay, you have Coke, you have orange juice, you have whatever. Then multiply, then you can eat 4 years without any problem. Okay, just for this single store. Okay, without anything else. So is it good for this one? So lastly, so we are over a little bit, but let's finish this because we can start the new one. So we're quick, even the same as before, but in the sense that we'll consider these 2 are the same, right? Then how do you count them? Okay, this is rather simple. In this case, is you double count by choice because for every possible thing, right, you can swap, right? So basically, just like you have 45 sandwich, if you look at the last question, it's 90 because everything is double count. You divide by 2, then you're done. Okay. Why divide by 2? Because you can swap, right? So for every is swap, right? But this is how you swap. It's just 2p2, right? 2p2 is just 2. Okay. So that's why how these 2 are related. You divide by r factorial because for every possible permutation, right? You can rearrange it. You pick r bar there. The r bar can rearrange itself. So that's why you double count by r factorial times. So that's why it's called NCR. Okay. So this question, again, motivated by my experience in the canteen. Now it's finding it's called the I think now it still exists. It's called budget meal in all the canteen here. I think it charges you $20 now, but in my days, only less than $10. In a CC canteen, it's $9.90. I think in the canteen, Franklin canteen, they have $9 to $10, depend you want different thing. They also have rice and noodle. That's very good fun because you can swap. And then you have sausage, spam, ham, and egg. Okay. And I remember the old day, it's pretty good fun. Anyway, it's a black and white sauce, pepper, or I think the cream sauce. And then ask how many different types of meal. Do you know that why we need combination? Because if I have sausage and ham, there's no difference for ham and sausage because you have a plate, right? And usually they just give you rice there, and you have some put the sausage here, maybe some vegetable there, right? And then you some egg, right? That doesn't really matter left and right, to you, I guess. Most of us don't really care left and right when you eat, so that's why it doesn't really matter. Okay. So in this case, how many times is we're combining counting and combination, right? The two ways to choose rice or noodle, that's two here. Two sauces there. But how many different ways to pick this? 4C2. Okay. So we have 24. Okay. So just bear with me one more minute because I want to maybe I should give a break first. There's no point to hurry. Let's have a break of 10 minutes and then we come back. Later I'll put the answer or reference, but it depends on how fast it's going. I try to because the is not just for our benefit. It's a TA for many classes. I put the answer on that. Is it okay? Because I don't really know how fast she can do the thing, but I can try to hurry. But I can put the answer, but it shouldn't be difficult. But if I forgot, just email me. Hi. So let's resume because we quickly finish this and then we can go to the next one. So here we have a question we told con 4 times. I think in the assignment we told 5 times anyway. But so what's the probability of getting exactly 2 tails? Okay. So that is a very classical problem. And the question is each toes would have 2 outcomes, right? Okay. What we do is because a fair con, so we do the calculations as a fraction, right? How many outcomes in the total, right? As a denominator, you have 4 toes, okay? Which means there's an emission of 4 tasks. Each task is have 2 outcomes. So 2 times 2 times 2 times 2 is 2 to the power 4. So which is 16. Is that okay for this one? 2, 2, 2, 2, 2. Okay. The next one would be we're asking is exactly 2 tails. Okay. So this one you may ask, how is it related to drawing a ball, right? Because nothing is a ball there. Okay. So we have to think in this way. I think it's easier to think in graphically. Okay. So for our purpose in this case, right? You have head, tail, head, tail, head, tail, right? So basically is the following, right? You have, so you can represent the outcome of this 4 thing is either head or tail here, head or tail here, head or tail here, head or tail here, right? That's why 2, 2, 2, 2, right? So the question is, we'll consider how many exactly 2 head, right? Count how many of them, right? So basically, it's just asking is, I have 2h here, don't know where, 2h, and the other must be tail because exactly 2 head, right? It means the other must be tail, right? So basically, exactly 2 head means exactly 2 head and exactly 2 tail. Okay. And when you tell the head, you already had the tail, right? So you can represent, say, for example, head, head, tail, tail. Okay. This outcome by thinking in the following way. Okay. Suppose this is the outcome. We can think about this. We have 4 different balls. Okay. If I draw the first, we'll say to draw the first ball, which means that the first one is head. First one is tail. Sorry, we call it tail, right? So it's tail, tail, head. That's better. because of tail, right? Okay. In that case, to represent this case, same as I draw two balls, the two balls are 1 and 2. If I have, say, tail, head, same as I draw two balls, which is 1 and 3. They're the same thing. Okay. So because I have each thing is two outcome, head or tail. So which is same as I can represent this as I have 4 different balls. If I say a tail, which is the first toes, we will draw number 1. If I have 2, this case, we have 1 and 2. In this case, it's 1 and 3. Okay. The question is same as 4 balls. I only draw 2 balls. Okay. And if you draw 1, 2, it's no different from 2, 1. Right, the same thing. So that's why the same. So that's why it's a combination. Okay. So that's why it's 4C2. Is that clear why we are doing this? So let me repeat because it's so important. I don't want you to miss this part. It's because in this case, okay, why we can write this way? Because for each possible draw, it's either 2 outcome, head or tail, right? And when you have this case like tail, head, which means that you can correspond to have 4 balls. I draw 1, 2 or 2, 1. Right? In this case, will be 1, 3 or 3, 1. Okay, but I don't care about order, right? So that's why it's when you try to draw 2 balls from here, we disregard the order. How many times you can draw is same as this one. So these two are the same problem. Is that clear? Is that okay? Is that okay for everyone? Because this is a little bit, your mind has to twist a little bit before you can understand this one. But once you twist your mind enough, then it becomes very straightforward to you. Okay? Because I twist my mind already, so I don't know how difficult now you are. It was difficult for me at that time. I twist my mind many times before I understand this. But not sure you immediately understand. But this thing, I mean, probably do some exercise, you will know a little bit more. But this is how this is being done. Is that okay? If you are not convinced, then you can just list all the outcome and try to connect each other. Then you can convince yourself this is the correct thing. Okay, that's how you solve this mathematical problem. It's the same thing. Of course, for those who do Math Olympics, then there's something you learn it in the early stage. Okay. So let's go back to this question. 4C2 is 6 out of 16, so that's why it's 8 out of 3. Okay. So at the very end, just to remind you a little bit about we do principal counting and permutation combination. How is this related to sampling? Okay. When we talk about sampling without replacement, it's similar to actually we're doing how many number of sample we have is actually for a principal counting. And if you have ordered sample, order matter, then it's permutation. When you unorder, it's a combination. Okay. But it's technical, so those things is gray. You can just relax. Okay. The video links, if you are confused, you can watch them again. I think it's not a big deal. Very short, I talk about Excel and R because for this chapter we don't have a lot of things to do R and Excel, except the fact that we need to learn some combinatorics because other things are just calculation by hand or calculator, right? So that's not much thing. So fact is the factorial. Later we'll show you the Excel quickly. Permutation with permu and combination combine. So this NCR and NPR. Okay, let's try to show you the Excel very quickly because I don't think we need to wait until Friday to do this part because wait until the Wednesday to do this part is so trivial. I don't think you don't really need. I just show you this formula only because there's nothing deep there. Okay, if factorial is just factorial, say 10. As I promised, it's a big number, right? 10 factorial. Let me show you the test. Okay. So that's why you have factorial, because even 10 factorial is a huge number already, which I have promised. The second one is NCR. So M.Phil is per mu. Per mu, say 10C5, say. Okay. It's again a very big number. Okay. So even though could you take 10 items or 5 items, that would be needed. Okay. So just this remind me the one other example when you do permutation. Okay. One other application is when you take group photo. Okay. Then we have person number 1, number 2, number 3, number 4, right? And then you will imagine how many different ways you can take picture, right? You can keep taking pictures, right? Group pick. We union take pictures, okay? Then how many different ways to take it, right? And you say left and right different, right? You position A and B and C, if you swap people are different, right? So this is combination, right? So if you now if 5 people can take picture out of 10, so how many pictures you can take? Huge number, so you can never end. Okay. And look at the case where you don't care about the order, it's combination. Let's do the combine. 10, 5, okay? They're much smaller, okay? But even that, I mean, you don't care about order, just care about this. There's how many different ways you can take pictures. Okay? So that's the reason why when you go to ceremony or stuff, you always take 1-to-1, right? The guy gives you the prize and you just take picture with that guy, not taking group picture all the time. Otherwise, you take forever. Look at this question, okay? Only 10 people, just do 5 people take picture, take forever. It never ends, okay? So is that okay? And lastly, I want to show the R. I think that is something, again, is trivial, but I just do it, okay? Factorial, it's just factorial, okay? There's nothing. And interestingly, there's no basic permutation in R, so just do the by definition. Of course, you can write your own function, which we'll talk about that on Wednesday. We'll talk about some. And the choose is NCR. So let me quickly load our studio because there's nothing special here. Oh, I don't think I can show you because I don't think they have our studio in this computer. But I hope I'm convinced you this is correct. Okay. Is that okay? I don't think there's an issue. I don't think I need to do this, right? I think you can do it by yourself. I mean, this is nothing. Just put the number there. Okay. I hope it's okay. At our stage, I think your computer will be much better experience than I do. Okay. Is there a question for this whole set of slides? It's probability. If no, then we go to random variable. Okay. Random variable is advanced version of probability. Not advanced, but a more elaborate version, I would say. Any question? If no, then we go to random variable. Okay. Now random variable, you see a lot. Okay, but don't worry, it contains at least half of the pages proof, and we just cover only 1 or 2 proof, the most simple one. The rest will be yours. We're not going to do any proof, okay, except 1 or 2, which I think that give you some flavor of them to prove. Okay, and the rest will be just for those who are interested in the proof. Or you can ask me or ask the TA for the proof, but or look at the video. The video have all the proof there. So you want to read, you can just go ahead. Okay. Our main idea is going to give you the how to do the calculation and how to use the software to do things. Okay. So of course it will be reflected by the assignment 3. Okay, it's too far to talk about assignment 3. I think this assignment 2, but that would be something you will learn what you will be doing. But is that okay for the? Well, don't worry. Assignment 2 will be not difficult. Okay, just 2 pages, but it's not something difficult. I think random variable have 3 pages, but anyway, but don't worry. It's very straightforward. I mean, it's not tied to be tricky. Okay, so the random variable, we learn probability. So the question is why we need to learn random variable, right? We're done, right? So we learn everything about probability. Yes, that's true. But you can see that how we describe the probabilities. We need a sample space. We need to know all the outcomes. And we calculate event. All this kind of thing can be tedious. Okay? Imagine this case, right? Even toasting a con many times. Here is how many you have, right? 2 times 4 is already 16. If you have toast 10 times, this will be a huge number, right? I mean, 1,000 something, or even toast 10 times, right? Then it will be difficult to handle, okay? So can we simplify the sample space? Okay, that's the goal. Okay, let me repeat again. What we're doing is the sample space in general will be huge and large. Okay, can we simplify it? Okay, and actually we have been doing a lot of simplification in the way we look at the world. Look at the stock market. In Hong Kong, I think there's more than 1,000 of stocks. Okay, then you talk about what the stock market is doing. Okay, you ask the question, what's the stock market doing? What we're doing is we look at one thing, Hang Seng Index, right? It's very hard to. And the next question is, look at what is the wealth of nation, how a economy is doing. Okay, there are many aspects of it, but usually we look at 1 or 2 things, which is GDP or unemployment, right? So same here. We want to reduce the dimension, okay, to make easier, okay? And how to reduce the dimension in the sample space is we talk about numbers, okay? Instead of talking about this, we reduce, right? For this case, we actually don't care about how these are ordered, right? Head, tail, head doesn't really matter. Sometimes we only care about how many number of heads, how many of tail, and that's it, right? For example, if you are a coffee shop or restaurant owner, right? Maybe you care because I think there's one is doing IPO, is doing the Tam Zai Mai Xin, is the rice noodle, whatever thing, right? And if you want to buy it, you don't, for the sample space, right? You don't really care about how many shops are making profit and how many customer coming in this morning, right? You care about aggregate, how much money they're making, right? There's a lot of random variable there for relevant for investment, but at the end of the day, you only care about how much profit they're making. Only one thing, the number, right? It's very complicated. The set, you care about one number, how much they're making. Same here. We are going to say we're trying to transform mapping, we'll try to assign the outcome of random experiment to a number. The outcome can be very complicated, but we just care about the number. Okay. And as I said, right, random variable make our life easier. Okay. And the second thing I want to say is what we call support. Okay. That's a technical term, support of random number. Is you can imagine the sample space, right, is containing what are possible outcome. Support of the random number is what kind of number you can put in. Okay, that's it. Okay, and you easily see what is support. I mean, give you the example immediately. So depend on just, let me talk about this before I go to example. Is there are 2 types of support, okay, which we will study. The first one is the support is finite, the other is infinite. Okay, what is finite means is, say, we collapse it to you can count it 1, 2, 3, 4, 5. Okay, maybe just care about number of tail or heads. Okay, that is 0, 1, 2, 3, 4, 5, right? And the meaning of 2.5 people is no meaning, right? How many people are, right? And sometimes it's continuous without finance, right? How much profit the company is making, right? Between 1 million and 2 million, the intermediate value means things, then it's continuous. Okay, the reason why we need to distinguish these 2 is not because of they're different, because that's just because you need different tools to do it. because mathematics, when it's finite, then you can do normal addition, subtraction, that's no problem. But when you talk about continuous random variable, those who learn calculus, then you need to, you know that because of continuous thing, you need to do integration and differentiation. Of course, in our class, we are not doing this. You want to understand the proof, you need that, but we're not supposed to do it, right? But we just still follow the traditional classification, okay? And because of we need different tools, things are a little different, you will see. But it's not crucial for our understanding, okay? But just give an example. I mean, still here a little bit abstract. Let's give you a more, I think it's more easy example. There's a typo here. There's a little bit typo here. Should be 0 and 1. So the question here is toss a coin. Okay, just start the beginnings. Very simple. Start a coin. The sample space is head and tail. Okay. Actually, we talk about this is already simplified a lot. Right? Because we talk about we don't talk about toss a coin. Where's the coin? When it land? Which direction it land? Right? We already simplified. But even that head or tail is still a complicated subject, right? But can we make it a number? Okay. And depend on the application, okay, how you change this sample space to number depend application, okay? It's not there's no hard and fast rule. It depends on what you need, okay? Suppose, as I said, right, you look at how you invest, you collapse the sample space to profit, right? That is what you care, okay? Here, suppose I care number of head, okay? Actually, in this case, there's no difference between number of head and number of tail. But when you have more toes, they will different. Okay. In this case, I don't care about number of head. Okay. So the random variable, okay, remember it's a function, is you give me the outcome, I give you a number. Okay. So that's why outcome is either head or tail. Head I match to 1, tail I match to 0. Okay, just repeat what I'm doing here. Random variable, it just say you give me the outcome, I give you a number. Okay, of course it's simplification, right? Because outcome can be very complicated. I just said, okay, the outcome thing, I just give you a number. Okay, in this case, how I simplify is I just count number of head. Okay, and in this case, I have 1 and 0. Okay, and that's why the support is 1 and 0. Okay, I don't know why I have 1 and 2, but just this. Okay. Yeah, the reason why actually I know this typo, but in the old days people print out the thing, and if I change, then they have communication which is the latest one. But I don't know whether I should update because anyway now because everyone using the laptop, so maybe next year I should keep always update the thing. But anyway, so that is the idea. So consider next case is I toss a coin twice. Okay, so we have 4 outcome, right? 2 times 2, right? Because principal counting, if head tail and head tail, right? And the question would be, okay, this is a complicated sample space. I want to simplify. Okay, what should I pick? Okay, in this particular case, I only pick number of head. Okay, but you can also pick number of tail. Okay, and in this particular case, you don't have a difference. Still, okay. If you look at this, if you have number of head, the number of tail is almost the same. Just 2 becomes 0, 0 becomes 2. Okay, but in that case, if your tail and tail is 0, head tail or tail is 1. So here is combo simplification. Okay, before we have 4 outcomes, now we collapse to 3 because it's only 0, 1, and 2. Right? Tail head and head tail give you 1. And head become 2, okay? And you do know that now your 3 outcome with 0, 1, and 2, right? So that's why support is 0, 1, and 2, okay? And the next thing is not all the outcome become equally likely, right? Before, if you toss a fair coin or fair die, each outcome is equally likely, okay? But now you don't have this luxury because you simplify it. Now, in the sense that you know 1 is more likely than 0 and 2. Okay, so it's no longer each outcome equally likely. Okay, it means that some outcome more likely than others, and you would form some shapes. Okay, and that is what we try to learn. Is there are common shapes to this kind of thing. Okay, there's a common pattern. Okay, before we don't need to need the pattern because most likely every outcome is similar, right? That's fine. But in this case, you can see it's more like a bell shape, or the middle is much larger. Okay, actually, you will see a lot of cases we learn, but the rest of this class is like it's like somewhat bell shape, but bell in which direction? Okay, so that is the idea in that sense, right? Here you can see the middle one has probability of 1/2 if it's a fair coin, and this 1/4 is 1/4, right? So that is something we'll be learning. Is that okay? Is that okay for this random variable? Just to remind you again, what random variable is, you want to transform the outcomes into numbers. No longer call outcome, we call numbers. Okay, it's a function of the mapping. So that's why it's we don't write this when you actually doing it, but in your mind it means that actually you're mapping the outcome to number. Okay, and when you say random variable equal to 1, actually there are maybe more than one outcome there. So just to bear in mind that this is something is very important. Okay, I can remember when I learned it, I don't really emphasize this when I learned these statistics in B school, but when I go to statistics department, they will emphasize this point. Okay, this is a very important distinction. So although we are still in B school, but I just want to remind you this is a very important step why we need to learn this chapter. Okay, because a sample space is complicated, we simplify. Okay, and how to simplify depends on your purpose and uses. Okay, and the next one is continuous. As I've said, continuous means that any given two values, any value in the middle makes sense. This is continuous. So temperature, stock market index, stock market price is non-negative, right? Price non-negative, and sample space is the first one, right? Come from physics, right? You know that the temperature of anything cannot be below this absolute 0. Okay, at least in this universe, we cannot be below that temperature. So that is a standard when I talk about the sample space. And when you have a unit dimensional, one-dimensional measurement, the support is exactly same as what you see, right? So that's nothing still to simplify in this case, right? Because you know the sample space is exactly the same as support. Okay. In that case, the stock market index, okay, is a real number. Okay. So in that case, you don't have too much to simplify. Okay. But here actually I'm cheating in some sense because I said beginning, what you care the sample space should be the whole market, right? Look at the whole market. But you are actually basically stock market index is a collapsing different price movement of different stocks into one single doesn't exist, the market portfolio, right? The Hang Seng Index, right? And that's exactly what actually doing, right? Hang Seng Index itself is in fact a random variable mapping from what happened in the other stock, right? Because there's nothing in the real world that's Hang Seng Index thing is moving, right? The real world is actually all the stock are moving, and you are just trying to capture the idea of how the stock market is moving through the Hang Seng Index, and that is the random variable mapping from what's happening in the real world into that one. Okay, and again, why you want to care about Hang Seng Index because it's much easier to know, right? Rather than looking at tens of thousands of stocks. Okay, is that fine? Okay, so I hope that's okay. If no question, then we go a little bit further. It's okay. Why we care about random variable? Okay, so we start with discrete. Just to remind you, discrete is you can count them. Okay, the reason why I start with this is because it's easier. We can do addition, subtraction, multiplication without any issue. Okay, otherwise we need to talk about limit, differentiation, integration. Okay, but let's get started. Okay, so now the thing is now we have a number. Okay, no longer we have a sample space become number now because we simplify. Okay, With a number, then how can you describe that? Okay, because what we want is, again, the probability, right? We want to know for each value of the random variable, what is the probability? Okay, say the random variable x can be number of customers, right? Maybe 0, 1, 2, 3, 4, 5, up to many, right? And the question is what's probability of one customer is coming, 2 or 3 and 4, right? So the very basic thing is you can see what we call the probability distribution function is asking, is say you give me the number small x, which is 0, 1, 2, 3, 4, 5. What's probability that this random variable is equal to that number? Okay, just remember, just go back to maybe go to the example immediately. Okay, here we have rolling a die. Okay, we have 1, 2, 3, 4, 5, 6. It's a fair die, suppose. Then in that case, this p of x, right? The probability that the random variable x, which is the face value, okay, is equal to 1 to 6, is just 1/6. Okay, and just to remind you, if you want to look at this question of say this one, okay, then the x is equal to 0, 1, and 2. Okay, and p of 1, okay, we have p of 0, p of 1, and p of 2, right? Suppose this is a fair coin, then p of 0 is 1/4, right? P of 1 is 1/2, and p of 2 is 1/4. Is that okay? Is it okay for this one? Okay, just in case you don't fully follow, but this is just nothing but just why this called a function, because it's just like you give me a number, I give the probability. Okay, just to remind you that what is this, the first one, p of x is you give me what number, I give you probability. Okay, that's it. It's okay. Now the second thing is cumulative one. It's asking not exactly this number, but what this number and below. Okay, just give you the example for this one. F of 0 is again 1/4. F of 1 is 3/4. F of 2 is 1. Is that okay? Okay, you may ask why is this one? This is probability x is less than or equal to 1, which is this plus this. Why is this 2 is 1? It's this plus this plus this. Is that clear? Of course, we have other example, which is somewhat easier. Look at this picture. F of 1 is 1/6. F of 2 is adding these two up. This guy. Maybe I just draw it here. Maybe easier to see. So if you're this guy, it's the sum of these two guys. Okay. And you have this guy, it's sum of these three guys. So on and so forth. I don't think I need to draw the sixth one, but you see the pattern there. That's how they're related. Okay. P of x is simple, just probability. F of x is a little bit more tricky. It's just sum of things equal and below. Okay. You may ask why we care about the second one, F, because this is the thing that when we define continuous random variable, and that is the key. Then we will try to draw the similarity. Okay. And sometimes people call this F called CDF. This is called PF or PMF or PDF, but this is called CDF. CDF. So this is something that's so commonly used. Okay. Now, I think it's good to draw a picture of this. Is it okay? Any question? Okay. And let's look at the picture. P of x in this case is this way, right? But when you draw this one, it's not that equal, right? We draw it's like this, this, this. What is, right? Because 1/4, 1/2, 1/4. This one is equal, but when you have this one, it's different, right? And for fx, it's like this, okay? But again, this one a little bit, I don't do it fully. In fact, if you are technical, okay, which we don't really assume you to do this, it should be like this. You should also draw this again. The reason why you need to do this is because asking is a function. What is from f of x, f of 1.5, right? Its probability x is less than 1.5, same as 1, because nothing between 1.5. So that's why you would draw a smaller step function. When you relook at the statistical textbook, you see this. But I think for our purpose, we are not math people. I mean, no one's asking 1.5 thing. I mean, except you are very serious person, right? But that's why I draw it this way. But of course, if you look at statistics book, they will see they will draw a step function, and there's this continuous jump over here. You have a hollow circle here. Here's a solid circle dot here. But anyway, I don't think we need to go that far. This graph is still correct. Okay, I just omit the things that I don't think is important. Okay. Same here, right? I don't. Same for the previous function here, right? I don't say actually it's 0 here, right? Because P of 4.5 is 0, right? Anything else is 0, right? So that's why when you usually people when they do this in math, I just show you. People would do, if you go to stat department, or I think they would call it this way. P of x is function if x is 1, they will do okay. That is a technical way to completely write down the thing. But this, if you go to statistics department, they will emphasize this guy. If you don't have this, then you make a mistake, because x can take any number, right? So that's why that's how they think about. You have to be very precise, but for our purpose, yeah, that's fine. Okay. I don't want to go to the detail because some of you may look at the textbook and ask me why I didn't do it this way. I just emphasize that we're trying to make our life easier. Of course, if you care, you would be concerned, then you should do it this way. Okay. Now, I think before we end today, we want to introduce you these two important concepts. Okay, is now with number. Okay, that means that actually we can talk about a lot of things, right? Because we know how to handle number in the first chapter. So that's why we'll combine the things we learned in the first chapter and now. Okay, we just do expectation and variance. We don't do kurtosis, but as I said, kurtosis is important when we talk about investment or other things. But just focus on the two simple things. The expectation is a mean, and variance is variance. Okay, so here is the question is expectation is a mean, and how it is related to the mean, what we learned from the first class. Okay, the connection is by what we talk about the classical probability. Okay, suppose we run this, suppose this case, we run this experiment many times. Okay, then you expect a quarter of them is 0, means there's no tail, right? And you have one tail is 1/2, right? 1/4 of all the outcome is 2 tail, right? And then you may ask, what's the mean of x, right? Then you just like 0 times a quarter plus this and this time this, right? So that is the outcome. It's a weighted average or just the mean, right? Let me repeat this argument because I think that's not in your mind is not that straightforward. This one is actually a way you can imagine the simplest thing is to think it's a weighted average, right? It's the value x, right? These are the weighting, okay? And you may ask what's the denominator, because the probability, some of them is 1, so we divide it by summation px is 1. Okay, this is weighted mean. Okay, first thing is the weighted mean, and it's weighted by probability. Okay, the second thing we ask is why this definition makes sense, right? Why weighted by probability? And in fact, it's just like you do the random experiment. Okay, you repeat many times. Okay, and 1,000, suppose 1,000 times, right? And then you'll be 2050 will be 0, right? With 5,000 will be 1, and again 2050 will be 2, right? So what is the mean of this, right? You will be, if you have 10,000, right? You will be doing this, right? 0 plus 0, right? You have 250, right? And then you have 1, you will be 5,000, right? And there will be 2, 2 will be 200, right? And you over because 10,000, right? But if you look at this, and this over this is probability, right? So basically this times probability plus this time probability and this. That is the mean. Okay. So intuitively, it means that actually we run this experiment many times and calculate the mean of x is the expectation. So that's why it's a mean. Is that okay? Of course, you don't have to realize this definition, but just explain to you why this makes sense. Okay. I mean, I think it takes me quite a long while to understand this, why this would make sense, but just definition. Because expectation is just you put this number here and put the probability. There's nothing. Okay. And we usually have we call mu of x. We longer x bar because when we talk about the data, sorry, we talk about the random variable, we usually go use the mu as a mean instead of x bar. Okay, just the notation. The second one, okay, that's nothing different from what we define variance. Variance is a square difference from the mean, right? It average square difference from the mean, right? Because you sum of them and divided by n, right? So that is the same idea. Is that expected difference from the mean? Okay. But look at again the definition, right? It's just like different from the mean. Remember, there's a number, it's a mu x, okay, and square and time probability. Okay, let's go back to here. What's the variance, right? You can calculate the mean, right? And each time you subtract the mean and square, right? Do the same thing. So that's why you have this formula. Okay, so that's why it's called sigma x squared. Is that okay? So this is a little bit trickier, but I want you to understand why we care about mean and variance in the first few class. And now we come back to here. They're the same thing, okay? Except that we keep imagine we keep running an experiment. You all got our data, you calculate again. This with the mean, this with the same thing. Okay, except we don't run the experiment anymore. But hypothetically, the same thing. Okay, we don't have data, but imagine that in our mind, we run this experiment and many times for data. Expectation is the mean. Variance is the variance, of course. Okay. Is that okay? Any question? For the remaining 2 minutes, I want to talk about this, and then we end. So what is the mean of rolling a die? It's very simple, right? Just you multiply each outcome with probability, right? And each outcome is 1/6, so it's 1 times 1/6, 2 times 1/6, so on and so forth. Okay. Here is simple because everything is 1/6. Okay. Same as our expectation is 3.5. So this is the same as the mean of rolling a die. Right? If you roll a die many times, right? If everything up here 1/6. Okay. And variance, okay. will be what expect, right? Each number minus the mean and square, and each outcome is 1/6, and that's it. Okay. Any question? I don't want to go further because there will be some people who have to catch a bus. But in case any question, concern, just to remind you again, I think Wednesday we will be using the lab. So we will be continuing this chapter, and then we'll talk about immediately we'll talk about some doing some R and Excel. And probably we'll finish the R that we didn't do last time, because we have something left on the first chapter on the R. Okay, we'll talk about functions and how to do program. Okay, after the Wednesday, you can put your CV, some R, because we'll do some real R stuff. Okay, on Wednesday. So see you.